Welcome everybody to another episode in the Head Acoustics Educational Webinar Series. My name is Jacob Sondergaard and I will be your host today. Today's topic is Noise Suppression Measurement Techniques, Part 1. So, as DSP technology has become more cost-effective to deploy, it's also become possible for communication devices to use some of this power to actively suppress background noise in voice calls. Obviously, hopefully, this has improved the quality of our voice calls significantly in the last couple of years, provided that the noise suppression techniques have been implemented to only reduce the noise and not affect the voice. So today's topic is really about how do we quantify how much noise suppression has been applied, and how do we potentially evaluate its impact on the voice quality. The whole goal being we want to make sure that the voice call is indeed better when we have noise suppression applied and that the voice call is not worse. So there are many different noise suppression methods used in voice quality testing, and today's session has therefore been split into two parts. Part 1, today, we'll talk about fundamentally why is noise suppression important. We'll paint a nice little picture, give you some examples. I think everyone will be clear on that. We'll dive into a couple of the single value metrics, so the Devalue, the ANR, ambient noise reduction, and the SNRI metrics, so signal to noise ratio improvement metrics. Then we'll wrap it up, put a nice big bow on it, and send you guys on your way. So let's start with the big overall picture and give you an example from the automotive community. You don't have to be in the business of making hands-free systems for vehicles or radios for vehicles. You could be making any type of product. So this example is really pretty universal. But it gives us a nice idea, especially with the baked-in audio files, of why it is important to have noise suppression or noise reduction. So in the automotive hands-free case, the number one thing is, of course, you don't sit in an anechoic chamber and make a phone call. You're in a real moving vehicle. There's lots of background noise. It could be raining. Your windshield wipers could be going. If you're driving X miles an hour, there is probably some tire noise. There may be some engine noise if you are in a good old-fashioned combustion engine vehicle and not one of these fancy electric vehicles. There's a lot of potential noise sources, and they totally depend on the type of vehicle as well. Typically, the more expensive a vehicle, the more care has been taken to dampen the acoustics in the car, things like that. But in general, noise is going to be present everywhere. Now, the cool thing, of course, is there is a psychological effect where if you put somebody in a noisy environment, they will talk a lot louder. That's what we call the Lombard Effect. So if you've ever paid attention to this, if you listen to somebody you know very well, a spouse or a friend or a colleague, and they're just talking on the phone in the office, listen to how loudly they speak when they're on a call. Now, take them out onto a busy street corner or a cafe and have them make a phone call again. Pay attention to see if they raise their voice. It's an involuntary effect that people just talk louder when they are in the presence of background noise. Now, from our perspective, making, tuning, testing devices, that works to our advantage. We get better SNR. And so if we take calibrated speech, measured at the mouth reference point, we produce some background noise of a certain volume, let's say 69 dBA, equivalent to a medium-sized vehicle driving at highway speeds. You end up with an overall speech and noise file that sounds a lot like this file that I'll play for you guys now.
The juice of lemons makes fine punch. A large size in stockings is hard to sell.
So what you might have heard there was a couple of different utterances with some road noise over the top, or in the background rather. Now, a fair warning, GoToWebinar does have a built-in noise suppressor, so it may have taken the edge off the background noise, but the point is, this is a very typical scenario. Now, in a vehicle or in a hands-free case, we are unfortunately in a situation where it is not safe to put a boom mic from the ceiling right in front of the driver's face. If you ask the hands-free team in all the automotive manufacturers or the radio designers, they would love the ability to do that. The designers, probably also the safety guys, would not allow them to do that. So microphones in a vehicle are typically placed in the visor and the headliner and that console in the center of the vehicle and the roof. And what that means from our perspective is acoustically, the speech coming out of our voice now has to travel a lot further to reach that microphone. And so ultimately, we end up dropping our SNR. And in some cases, directionality plays an issue if the microphone isn't placed somewhere roughly in the speech projection path. So that works to our disadvantage. Now, on top of that, we're not exactly using the high quality measurement grade microphones for our applications. It doesn't matter what type of product you make, any type of mass produced product, you're going to find relatively inexpensive microphones that will have an imperfect frequency response. And in some cases, in an analog fashion, have been tuned or designed to simply cut off at certain frequency ranges. It's not uncommon, especially for vehicle applications and mobile phone applications, to choose transducers that simply don't have any sensitivity at the very low frequencies. The two primary reasons for that, so in this case, roughly around 300 hertz, the two primary reasons for that in a vehicle situation, a lot of the driving noise is actually similar to a pink noise spectrum. So it's very low frequency dominated. There's a lot of energy in the low frequencies in a vehicle from a noise perspective. And if your microphone from just an analog perspective just isn't sensitive to that, great. You have to do less DSP work. You've taken care of a lot of the noise suppression using physics. Now, for a mobile phone, if you're anywhere outside and it's just the tiniest bit windy, or you're moving, you're walking, you're biking, you're doing something, you'll know that wind noise is a big factor as well. And that is something that will, again, make it a lot harder for a noise suppressor to counteract. So in many cases, you'll see that microphones will have a low frequency cutoff that can help us later on. Now, the problem is, well, one of the benefits is most human speech exists above 300 hertz. Not all, but most. So it doesn't really impact intelligibility, but what it will do is the voice will sound muffled. So let me play you another file here, another couple files, just to show the progression of our audio path.
The juice of lemons makes a fine punch.
A large size in stockings is hard to sell.
The juice of lemons makes a fine punch.
A large size in stockings is hard to sell.
Right, so hopefully you're getting the sense of this is not really working in our favor from a voice quality perspective. Now, if you add to the equation that our voice signal has to pass through at least one, and in a hands-free case, potentially two different codecs. So we're going from a Bluetooth to an RF codec, two different codecs, we can end up with a significantly degraded signal that will impact our intelligibility and our quality. And then at the very end, what we also have to remember is we need to apply some noise reduction and some noise suppression. So let me just play you these last two to round off the example, and you can see what the noise suppression will do to our audio signal.
Juice of lemons makes a fine punch.
A large size in stockings is hard to sell.
The juice of lemons makes a fine punch.
A large size in stockings is hard to sell.
All right, so what you might have heard in the last two is simply that the noise suppression goes in to suppress the background noise, improves the signal to noise ratio without giving us any reduction in voice or speech quality. And that's what we want to see. That's the purpose of noise suppression that we want to apply. But the big question is, how do we go about measuring it? So a lot of the metrics that we'll talk about today have been around for quite a while. The single value metrics are the ones known as Devalue, ANR, and SNRI. The Devalue comes to us from ITUT G111 and was a first approach at characterizing noise rejection as opposed to noise reduction. And I'll go into that in a little bit. But it's been around for quite a long time, and we'll talk about it today. ANR, similar thing, it's a single value metric, very closely resembles the Devalue calculation and measurement. And ANR stands for the ambient noise rejection, not to be confused with something like ANC, which is something that everybody's probably familiar with from consumer headphones and maybe even vehicles. ANC, of course, is the active noise cancellation, something that's applied in the what we call the receive direction in telecommunications, but in the listening example for audio. So the two are actually not related at all, and I want to be sure that we're talking about the right thing where everybody's on the same page today. We're talking about the ambient noise rejection, which you can find in the TS26 132 standard, one of the older versions, mind you, version 11. I think we're up to version 14 now. TS26 is the mobile phone test standard. And then an additional single value metric is the SNRI, which comes to us from ITUT G160. And SNRI is the signal to noise ratio improvement. Now, if you have noise and speech mixing in the real world, these single value metrics are not the only ones we can use to evaluate how good the noise suppression is in a device. First of all, it is a tricky endeavor, but we also have something called the background noise transmission, or BGNT, which we can apply in both the uplink, so the sending direction, or in the downlink direction, the receive direction. It's described in the ETSI. So that's ETSI is the European Telecommunication Standards Institute, or body, that governs both mobile phones and voice over IP communications in the two respective standards. There's references there to BGNT. Additionally, we can use MOS-based metrics like 3Quest, which also look at the speech quality element during background noise. So because we have so much content to cover, today's session is focused on the top three single value overall metrics, Devalue, ANR, and SNRI. And it's important to mention that none of those three, nor BG&T for that matter, actually include an evaluation of the voice quality. These metrics, the top four, are really only looking at the noise suppression element in a voice call with background noise. So let's start with the first one and peel back a couple layers here, because if we look at Devalue, the fundamental aspect here is we're looking at the device's ability to reject noise. And as I mentioned earlier, we talk about noise rejection and not necessarily noise reduction or noise suppression. So noise rejection is actually something that's more of an effect in the real world rather than some DSP implementation of an algorithm. So the image I want you to conjure up in your brains right now is the old style analog handsets that would have a nice mouthpiece that would go up right in front of your mouth and in some sense act as a physical deterrent to the noise. So the microphone in the handset would be firing right into your mouth and picking up whatever speech came from your mouth while physically acting as a blockage to outside noise. For that, we would say there's a lot of potential noise rejection in the physical shape and design of that handset, and that's where Devalue comes into effect. The fundamental principle of Devalue is we measure what we call the sensitivity of the diffuse noise. So that's what we call background noise. And we look at the delta between that and the direct noise or the direct sound, which is the speech. What's interesting here, of course, is we do this separately. First, we take a measurement with noise only, and then we take a measurement with speech only, no noise. And then we compare the sensitivities of each. There's a weighting curve that we need to apply. But otherwise, we get the phone's ability to essentially reject background noise. And again, it's important to note, there is no element of voice quality analysis here. This is really just looking at how sensitive is the phone towards transmitting background noise. Now, ANR, or the ambient noise rejection, very similar to Devalue, although we apply a slightly different weighting function, and there's a slightly different measurement technique as well. We'll get into that in a minute. But you look at the ITU-TG 111 for the details, you'll see that we essentially do the same thing. We look at how sensitive is the phone to diffuse noise and the direct noise, which is the speech component. And then once we have those sensitivities, we look at each third octave band and apply the weighting curves to give us an idea of how well the phone would perform in a noisy environment. So as I mentioned early on, 3GPP, so the TS26 standard version 11, pointed to this, but it's long since been removed from the standard. We don't include this anymore in 3GPP. So from a very high level perspective, if we take a look at the block diagram, you can see that the top input on the left hand side, what we call the diffuse SSI diff, the noise component, that's the frequency response. So basically a frequency response function of the noise. We subtract that from the SSI direct, which is the speech, the clean speech coming out of the hat's mouth. We look at the delta and we apply our weighting curves, and we have, once we sum up each third octave band, we have what we call our D-value or our ANR. Now, I've been doing this for a little while, and even glancing through the standards like G111, and the old 3GPP, I have yet to figure out what D in Devalue stands for. So before the questions start coming in, I just don't know. It's not clear to me in the standards. In any case, Devalue and ANR is the resulting output of our calculation that we use to figure out how good is the noise rejection of our devices. Now, let's look at the physical setup for measuring these two parameters. The first thing we do is we record some background noise with no speech. That's what we call the diffuse frequency response. And then we measure the speech, but with no background noise playing. And we're doing that using a reference microphone. Then we repeat the exact same step, but we now use the device under test phone. So a mobile phone, for instance. And once we calculate the frequency responses for both diffuse and direct modes, we can apply our weighting curves, sum up our power bands to get our final values. Now, before we get too excited about this, I want you to think about modern devices with built-in noise suppressors and how such a device would hold up in a noisy environment with no near-end speech, which is the test method for both Devalue and ANR. And you think about how easy it might be to manipulate these metrics with modern technology. Right? The fundamental flaw here in the setup with modern devices is that speech with no noise should result in very nice speech reproduction, good frequency response and all that. There's really nothing that we're doing to the speech if there's no background noise. And conversely, if we have noise but no near-end speech, this noise suppressor in our modern device should be kicking in at maximum and just suppressing the heck out of it and giving us very low signals. So when we talk about, the sensitivity of the transmitted signals of speech with no noise versus the noise with no speech, modern devices should really ace this test without any issues. And so in rare instances will you be forced to take a look at these measurements, and at this point you can say, oh yeah, I remember the seminar and the video from Head Acoustics. Great, I can go look it up there. For those of you guys that don't have to look at this, check the box. You know what it is. You probably may not have to get back to this, but this is what we've been doing for a long time in the telecommunications world. So just to wrap up these two metrics, Devalue and ANR, let's start with some of the negatives here. The number one thing is we're not measuring any elements of speech quality, right? So there's another easy way to trick this metric is simply to have maximum noise suppression regardless of what's going on in the phone and in the acoustic environment. And that would lead you to great Devalue and ANR scores, but you have no idea what it would do to your speech quality. So these values are far from, or these metrics are far from complete. Additionally, even in these narrow circumstances, they're still not that good if you have background noise that's relatively transient. So something like driving noise, pink noise, okay. But if you start talking about the newer, more commonly used background noises like pub noise, road noise, traffic noise, things like that, where there's a lot of directionality, moving parts, and transients, these values just don't really hold up too well anymore. Now, of course, some of the good things is we have very well-defined standards written around them. They give you that single value, which is a great way to compare different builds or different versions or different products. And to be fair, if you have steady-state background noise, they do work relatively well. Now, remember, all we're doing here is measuring sensitivity of the speech signal, the direct sound, and the noise signal, which is the diffuse sound. Let me play you these two different samples, different devices that we've measured, and you can see for a d-value of 19.5, how good does the speech signal sound? And remember, we're not really talking about, I'm not asking you to evaluate the speech quality here. That's not really a measure that we're looking at. We're just looking at the speech volume versus the noise volume. And then likewise, on the right-hand side, I'll play you a product that has a d-value of 1. Basically, speech and noise is roughly equivalent.
The stray cat gave birth to kittens.
The pirate seized the crew of the lost ship.
The boy was there when the sun rose.
The fruit of a fig tree is apple shaped.
The box was thrown beside the parked truck.
8 miles of woodland burned each way.
Mend the coat before you go out.
The urge to write short stories is rare.
All right, so clearly there's a difference in how much background noise is transmitted. And what you could really consider these d-value and A&R metrics, it's a very crude way to evaluate signal to noise ratio in a device. Which brings us to a little bit more of a modern day metric, which comes to us from ITU. So this is SNRI, or signal to noise ratio improvement. This was designed specifically as an evolution to D-value and A&R. It really was looking at an improvement in evaluating SNR improvement, signal to noise ratio improvement. The limitations again is that we're not looking at the voice quality aspect. We're still just looking at how good is the noise suppressor in the phone, but we're getting a lot more sophisticated about it than what we did with the D-value and A&R metrics. Another key point that I want to mention is that this was originally designed for sort of a board level chip noise reduction or noise suppression algorithm purpose. It was designed for electrical measurements and not for acoustical measurements. It wasn't designed to be used on a phone or on a vehicle or a complete acoustic test scenario, conference phone, whatever you're making. It really was designed for electrical measurements. There are some ways to get around it. I'll talk about it in a minute, but if there was ever a metric where documentation was important, SNRI is one of them. So when we look at G160, the ITU standard, what you'll see is that we actually get 4 individual metrics with the SNRI metric. So SNRI is sort of the shorthand for what is encompassed in G160, but SNRI, the actual signal to noise ratio improvement metric, is one of the individual 4 metrics that we get out of it. The SNRI is sort of the very quick overall high level perspective. How good is the SNR going into our device and how good is the SNR going out? ITU has said, ideally, we want to see a 4 dB improvement, and that makes sense. We would like to have our noise suppressor do some type of work for us that reduces the background noise and gives us a little bit more space between our speech signal and our noise signal. What we also get is something called the TNLR, the total noise level reduction. This is an interesting one where we use some frame segmentation to look at the speech and the noise portions, separating the two to only find the noise portions, or the silence portions rather, the silence between each sentence, and those are typically very easy to detect. They're slightly longer, but we also look at the very short pauses in between words, and then we sum up all those silence periods and we look at what is the total noise in those portions in the processed signal versus the unprocessed. And then we evaluate the noise suppression. And again, ITU says, ideally, we end up with something that's greater than 5 dB of total noise level reduction. So this gets a little bit more sophisticated. We also have another metric called the NPLR, which is the noise power level reduction. This is something that looks at the short pauses in between words only. So it looks for the active speech portion in our stimulus file, zeroes in on that active speech and says, hey, where do I have the slight pauses or the slight silences within this total active speech block? And then looks at the delta between the processed and the unprocessed signals to say how good is the noise suppression occurring in between words in a sentence. Now, the goal with the NPLR metric is really to look at whether our device is doing something called noise gating, where that noise suppression in between words still remains natural, still remains active, so that the noise suppressor isn't too aggressive and just attacks every bit of silence or every pause aggressively. The last metric we call DSN, and DSN is really just the difference between the overall SNRI or the overall noise suppression or the improvement in signal to noise ratio balanced with the NPLR, the noise power level reduction in between the short pauses, in between the words, the short pauses between words. So what we do here is we essentially look for a value roughly around 0. If you have negative DSN values, what that points to is that we are potentially attenuating our speech. And if you have positive DSN values, you potentially have some speech amplification going on. So you can already now see that this is fairly complicated and a big step up from the old Devalue and ANR methods. So I don't want to spend too much time on this block diagram, but we can sort of trace it together and see that we're not just talking about basic frequency response calculations anymore. This is a multi-stepped process where on the left-hand side, we start with our what we call our clean speech or our reference signal. We start with a speech plus noise, the noisy speech, which is what we would call the unprocessed signals, typically measured with a reference microphone. And we have the noisy speech that has been fed through a noise suppression or a noise reduction algorithm, which is what we would call our process signal. Now, this might sound familiar to a lot of you guys if you've worked with something like 3Quest. This is the fundamental 3-channel algorithm. In this frame classification, we'll split up the speech into different brackets. We'll find the noise portion, we'll find the active speech portion, and classify them into low-level speech, high-level speech, etc. Then we'll go through and apply some weighting curves, and finally calculate out SNRI, NPLR, TNLR, etc. Now, the big question, of course, is, well, how does this get applied to my speech signal? So let's look at what SNRI does in a real example here. What we're looking at is, first of all, a level versus time analysis of a utterance in noise. And the first thing we do is we locate the active speech. So you can see that we've already zeroed in and said between just about 5.6 seconds to about 7.8 seconds, we've located an active speech portion. Then we go ahead and look for everything that is below minus 51 dBOV, and we call that noise. So anything down here in the green is what we would consider the noise portion. Then we say, let's find all the speech between minus 36 and minus 42 dBOV, and we call that the low speech. We find the mid speech, and then we find the high speech. Now, what's shown here in gray are only in the active speech portions and are where the level drops down from high speech into something below it. That is the NPLR. And what we do here is we then sum up the energy in each of those gray columns, basically the silence in between the words during that active speech, to get our NPLR score. That's just the silence during active speech. Now, if we wanted to get the TNLR, remember down here, we also add the noise portion, or rather the silence portion, what is supposed to be silence, between our sentences. So then we have to add the signal down here, the noise, to get TNLR. So this is really just taking the previous block diagram and then we'll put some colors on it. Now clearly this is a lot more sophisticated, but it still fundamentally gives us a single easy value to work with. However, we do have those additional metrics that we can use for diagnosis. Let me play you these different files. So the unprocessed signal and then two different devices put in the exact same situation, and you can see whether you agree with the overall scores. Remember, SNRI is the total, hey, how well did we improve the signal-to-noise ratio? The TNLR, we're looking for the total attenuation in all the silence bits. The NPLR, we're just looking for the attenuation during the active speech and the silences between words during active speech. And of course, DSN, that was the balance between total SNRI and the NPLR. So let me play these three, and you can get a sense of what the metric is telling us.
He broke a new shoelace that day.
The box was thrown beside the parked truck.
8 miles of woodland burned to waste. He broke a new shoelace that day.
The box was thrown beside the parked truck.
8 miles of woodland burned to waste. He broke a new shoelace that day.
The box was thrown beside the parked truck.
8 miles of woodland burned to waste.
So overall, I think the metrics give us a pretty good idea of how much noise suppression is being applied. Now, of course, we still want to harp on the fact that we're not evaluating voice quality at all. So regardless of how much noise suppression was applied, we are still not considering the impact on the voice quality at all. And we still haven't really touched on what we need to do for acoustic testing, because there are a couple different methodologies that we have to look for. And I'm making an assumption that most of you out there, you have an interest in the acoustic side as well. If you are on the electrical side, if you make DSPs, noise suppressors, etc., then the SNRI metric is pretty straightforward and easy to use. You just simply measure the signal going into your noise suppressor or your noise suppression algorithm. That would be considered your unprocessed signal. And then you measure what's coming out. That's your process signal. You run the SNRI calculations and you're good to go. For acoustical testing, let's say you make a car or a conference phone. What do we do now? So you may want info on not just the noise suppressor, but we also want potentially noise rejection and what signals are going into your microphone. So our first step is, for an acoustic test, we have to define whether the reference mic that we're using is placed at the DUT mic location, that is the preferred location, it gives you the most accurate comparisons. But in some case, people put the reference mic at the MRP. Now that obviously makes for slightly easier mounting and setup and maybe also greater repeatability. However, not necessarily the most accurate, but this is open to interpretation. Now, the second step is we actually have sort of a choose your own path type of story here, because we can choose to do a measurement with the noise suppression off in our device, use that as the unprocessed signal, then we switch on the noise suppression and we use that as the process signal. That's great if you can control the device, but if you are a mobile phone manufacturer and you're just implementing this, you may not have control over it. If you're a test lab that are benchmarking phones, you may not have control over the phone, and we can't use that method. So the other way is to use something like a transfer function method, where we measure the send frequency response of the phone, and we apply that as a weighting curve to our unprocessed signal, which, remember, we're capturing with the reference mic. So we're trying to get the phone's characteristics applied to the reference mic. However, some people also use something like an MSIN filter. If you guys remember way back in one of our earlier sessions, we talked about mobile station in filters that are really just meant to replicate what a typical mobile phone terminal will do to a signal. And remember, we're applying this to our unprocessed signal captured with the reference mic. So we have options, but it's clearly not as straightforward as the electrical case. And a lot of these decisions have to be defined in advance. Now, let's take a look at our actual physical setup. So remember, we have to define the reference mic location. Are you going to be there at the DUT, or are you going to be at the MRP? It's not really standardized. The standard was never written around acoustical tests, so you have to make that decision. You have to document it, and you have to let other people know what you did. Otherwise, it's going to be really hard for them to duplicate your work. Now, secondly, on that reference mic, you have to make a decision on if you are using the reference mic. If you don't have access to the noise suppression algorithm on the phone, you have to let people know, are you using the SFR, the send frequency response, as a weighting curve, or are you using the mobile station in, the MSIN filter? That will make a difference. Now, finally, we will capture the process signal from the actual device's microphone. That's pretty straightforward. So from those three signals, we can then calculate the SNRI and the associated metrics that go with it. So a couple other things, couple words of warning here. SNRI is fundamentally a full band calculation because we're just dealing with the electrical domain, and we haven't really considered things like narrowband or wideband filters. Additionally, the different techniques I'll show you here can give you very different scores. So I won't play these audio files again. These are products that you've already heard earlier in the presentation, but what you'll notice is the scores differ dramatically depending on which filter you apply. Now remember, this is for the acoustic test case, where if we don't use any filter, our SNRI is around 20. If we apply the send frequency response filter from our phone to the unprocessed signal, well, our SNRI is still pretty good, a little over 18 dB. It's pretty good improvement. But you look at the other numbers, and especially something like the DSN, and you can see there's a lot of change there. And then if you also apply the MSIN filter to the unprocessed reference mic signal, once again, yeah, we're not too far off with the SNRI, but if you're looking at these other metrics, there's quite a big difference. And so it gets a little bit dangerous when you're doing SNRI for acoustics if you don't have any idea how somebody else did the measurement and you're trying to duplicate it. Now, for the other example, we used a fairly good product and a not so good product in today's session. And for the other one, coincidentally, the SFR and Empson filter actually stack up fairly well for this product, but there's no guarantee that this holds true for multiple different products. So we are in a little bit of a bind when it comes to SNRI. And this is where the documentation becomes critically important. So let's wrap this guy up. The messages that we wanted to leave you with today was that noise suppression usually means that we have lower noise and better signal to noise ratio. We want noise suppression. And we do have a couple metrics that used to be very good, so the Devalue and the ANR, but I think today it maybe dawns on everybody that there's probably a good reason why we don't use them so much anymore. They are not as applicable today. Modern devices can fairly easily ace those tests and those parameters. And then we talked about signal to noise ratio, which is the big evolution from ITU over Devalue and ANR. And there's a lot of positives with SNRI, especially for electrical testing. And we can even apply it acoustically, which is a big benefit. But it doesn't come without its pitfalls. Chief among them is the fact that we still don't evaluate voice quality. So with that, I would like to thank you for your attendance and your attention. We hope to see you for part 2 in the next session. And we want to wish you a fantastic day.